Good afternoon, everyone. My name is Jared, and I'm with Rogov and Manassa, and today we'll be presenting our project Stereo Image Depth Sensing. So a quick outline of what we'll cover in this presentation. We'll start out with a motivation behind our project, and then we'll discuss three different methods for depth sensing. For each, we'll briefly discuss the results, and we'll end with some conclusions. The basic motivation behind our project is that you have some manipulator robot that lives within some scene. We assume that this robot has access to a camera system that gives you both a stereo pair of images, so a left image and a right image, as well as a noisy estimation for the depth map for that scene. Our project scope is that we want to learn a deep neural network to map this data that the robot has to an accurate depth map. And we consider specifically a regime of low volume data, so only a few hundred data samples.
Okay, so the first method we tried out was direct depth sensing using a DispNet. A DispNet works using an encoder, which isolates the important features, and then a decoder, which finds the most important, where the important features are located, as seen in the diagram below. The loss function that's used multiple times is the mean squared error. And the idea of this method is to stack the left image on the right image and use those as input and output a disparity map. The motivation behind using this method in our project is to be able to learn important features and localize them and test out previous methods of depth sensing. The DispNet results, as you can see, weren't the greatest. The average correlation between the ground truth and the output is 1%. And our predictions as to why that is that the mean squared error gets stuck at some local minimum that's larger than the global minimum, which would be the ground truth. And this is because the encoder works, so it isolates the important features, but the decoder doesn't, so it can't find where these features are.
Cool. So our second method is image reconstruction. So essentially, we want to see if we can learn a disparity map indirectly by measuring loss on a reconstructed left image as opposed to directly on the disparity map. So given a right image and given a disparity map from a network, we should be able to reconstruct a left image. So the benefit of this technique is that it does not require ground truth disparity maps for training. The network we used is ResNet 50, and the loss function we used is MSE. So average correlation this time is about 7%, so it's better, but still not great. In particular, notice how the generated left image on the right, in fact, actually very closely matches the right image. So it's not really generating a left image. And this is because our disparity map is just not that great.
Another way to formulate depth sensing is as an image denoising problem. So essentially what we have on the top left portion of the slide is we have the noisy estimation of our depth map that our robot has access to. We want to feed that through a denoising network to give us an accurate, denoised, if you will, depth map. The denoising architecture that we choose to use is UNet. The basic architecture for this network is given in the bottom left-hand portion of this slide. The top right portion of the slide describes how we generated our training data. We basically just took the ground truth disparities and added noise terms to them, drawn from a Gaussian of mean 0, standard deviation 0.1. UNet is important because it works very well with low volume data. It has the encoder-decoder architecture, but instead of using MSE, it uses a pixel-to-pixel classification with binary cross-entropy. The results are very promising. The UNet output indicates a 70% average correlation with the ground truth as compared to a 34% average correlation between the noisy depth map and the ground truth depth map that you want. This is a clear improvement in performance, and it also outperforms the other two networks that our project considers. So while direct depth sensing can generate good results, if you have enough training data, as previous works demonstrate, they use hundreds of thousands of training examples. It doesn't work as well on smaller data sets. Image reconstruction does improve performance, and it has the extra added perk that you don't actually need ground truth disparity maps to train your network. However, like direct sensing methods, it also gets stuck in local minima, and this means that it doesn't generalize very well to the low data regime that our project considers. This means that the best way to conceptualize depth estimation is through an image denoising problem that uses a pixel to pixel classification. So this concludes our presentation. Thank you for listening.